Good morning. All right, well, welcome back to another week. Today we're going to continue with Chapter 6, and we'll hopefully complete Chapter 6 by Wednesday before your exam. If not, we have a little bit of flexible scheduling next Monday after your exam. Before we continue on Chapter 6 lecture, I just want to draw your attention to the exam modules, Exam 1 module and the study resources. So within this page, if you haven't seen it already, we've updated all the links to the resources that are online. Obviously, office hours recitations are still available, and you're definitely welcome to come to all of that. So this just puts in place just a review guide. So we have learning objectives for each module. So definitely be sure to go over that and ask yourself, can I do that? Did I learn that? Is that a point of confusion or something? And reach out to us. If it is, your lecture slides, recorded lectures are all updated for the 5 chapters. Homework, your TAs have uploaded the written out solutions for the homework. And they've only included the solutions for the computational questions, so that if you did get it wrong or you just want to review, they're all there. And then the top hat, obviously I've loaded a lot of the lecture slides with top hat questions that I did not get a chance to choose from, but the answers have been worked out and also compiled in one PDF for you. So just click on that link if you want to review. It's also a good way just to sort of use it as a practice exam in addition to the practice exam, okay? And the practice exam and its key are also uploaded as point number 5. And I provide this because it mimics the style of the exam that you're going to take on Friday. I don't want you to be surprised. We've talked about the style of the exam in terms of being split between conceptual and computational questions. So this gives you a good trial run for that, because we're all about transparency. It's not to trick you or anything like that. It's really just to test you on the concepts that we've talked about. So you have 2 opportunities to just run through and time yourself. I believe I've already talked with some of you in the front after class on Friday, but I just want to reiterate so that everyone's on the same page, which is your TAs have gone through the exam. They've taken it just like one would take, so that we work out all the quirks. If there are constants that are off or copy and pasted incorrectly or something like that, all the data values that you would need will be provided for you. And your TA, given their expertise level, I scale it based on how long it takes them on average to do the exam, and I scale it so that you can complete it in about 45 minutes, even though you're given 55 minutes, okay? So that's the expectation for the exam. Any other questions that I haven't answered? Okay. I should also mention, some of you came up to me to ask about a typo that was in the example for Chapter 5, the diffusion example for fixed first law. I emailed that out, so if you haven't received notification, you haven't checked into Carmen or your inbox, please be aware that the typo has been fixed. I've also fixed the meters typo. I mean, I fixed it in class, but your lecture slides, the PDF version, has also been updated to reflect that. So if you open it up, you'll see that the units from millimeters to meters has been changed and updated properly, so that when you're studying, you don't get confused by those little things like that. Okay, so we went through a lot of the terms. Let me just go back before slide 12. We ran through quite a bit of terminology to start off Chapter 6 on mechanical properties, and these are the terms that will go into depth today, particularly for the elastic deformation region as well as plastically deformed. Basically, when you've loaded your sample, applied the force, and now it's not recoverable. We'll talk a lot about that and how it enhances actually strength of the material. So let's go in depth. Let's see. Okay, so all that should have been updated. I want to start off with an example that takes advantage of mechanical properties of different materials, and of course it's within our own body. And so I found this plot from a tissue engineering journal, which is actually a journal that I don't often read, but it's actually quite useful if you're trying to understand body mechanics. And so what you see here is an example of the stress and strain curves for bone versus tendon. And so bone you can think about as being the majority of it is made up of, for all the BME people in the audience, bone is majority what mineral? Calcium carbonate is chalk. What's the anion? What's the anion? Also has the same 2- charge. Actually, it's 3- charge, sorry. But it's an anion nonetheless. Phosphate, yeah, calcium phosphate. So it's a ceramic, right? You got a cation and you got some polyanion. All right, so we talked a lot about cations, anions. Here, phosphate is a polyanion, so it's made of a phosphorus and oxides, but that's the majority of bone. So for all intents, purposes, and simplification, we'll talk about bone as basically a ceramic, okay? And so here you can see the difference between bone and a tendon. So here you see that the strength of bone is much stronger, okay? So you can see that if this is, let's say, the yield strength of bone, although the yield strength separates the elastic region and the plastic region, and you could see that for bone, there isn't really a plastic or a ceramic. There really isn't a plastic region. So what that means is your bone or your calcium phosphate is going to fracture, hopefully not rupture. It's going to fracture, and it will not plastically deform. You will just break your bone. But it is very strong. And so the strength is needed to obviously hold up your body, right? We can also see that the modulus, the Young's modulus, or which is a description of the stiffness, you could see that slope is much higher than that of tendon, okay? So when we're describing stiffness, when we're describing higher modulus or larger modulus, we're saying that it needs a larger force to deform, which makes sense since the y-axis is in units of megapascals or newtons per meter, and the x-axis is just unitless. And then we could also think about the strength. Okay, so I've talked about strength here. If we do the 0.2, let's see, 0.2% is somewhere near here. So if we were able to zoom in, I'm not drawing over the line, it's just 0.2% is very close to the line itself. Let's say we draw the 0.2%, then this would be the yield strength. That would be the definition of when your material stop being elastic and starts experiencing plastic deformation, okay? So that's the difference. Tendon can plastically deform by this definition. Bone cannot. You can compare two metals. You can compare metal and a ceramic, what have you, but these are the general differences. And then here we also see, if we take the area under the curve, that's what the grayed out area is, we can talk about toughness of a material. And so that's the amount of energy that is absorbed to break or at fracture. Right? So we integrate all the way up to fracture. And so for ceramic, there is no plastic deformation really before fracture. There are subtle nuance discussions about whether or not ceramics undergo plastic deformation. For this example and for this class, we would say there's no plastic deformation. And so you could see the area under the curve for tendon is much larger than that of the area under the curve for bone or a ceramic, right? So I would say tendon is tougher than that of bone, okay? And so later on in chapter 12, we'll talk about polymers and composites and how we can take advantage of these two disparate types of materials with two different mechanical, setup mechanical properties, combine them to make a composite and take advantage of both the strength and ductility of the two samples, or of the two components in a composite. But for now, we'll treat them separately. So we talked a lot about, metal, ceramics, but here's a bio example that's quite relevant. So if you ever take physical therapy, you can talk to your heart's content with your physical therapist all about the, fracture point of bone and such. So yeah, so you could see here the strength is about 140 megapascals, which is, not that high, by the way. Metals are like much higher than that, like 200, 300, up to gigapascal. So anyway, that's that. But you could see tendon, you can strain quite a bit before you basically fracture or tear your tendon. So that's basically the amount before you tear. Okay. So elastic deformation, now plastic deformation. The way one thinks about deforming the material, you could think about the atomic changes within the material. The option one, in terms of what happens when you're changing, you're applying a load, you're in tensile, so you're stretching your material. It's difficult to cause a simultaneous shift because that means you're breaking a lot of bonds simultaneously. That's extremely energetically consuming. So what typically happens is there's an incremental shift that you see in the cartoon with the green atom. So one plane moves and then it shifts over and it keeps on moving. So we call this the slip plane. This is the plane which it's moving across. And what you also see from this cartoon is that the overall length, if you count from here, where your material ended here before, it's now ending over here. So your overall length in the material is also increasing by a little bit, which makes sort of sense, right? Because you're straining you're applying some stress, and now that's causing some elongation, some strain increase. Okay. So we can take a look at that and talk about both we can measure the elongation of a material, but we can also normalize it to its original length and call that the strain. So as we talked about in the intro of this chapter, strain is actually unitless because it's the change in the distance divided by the original distance. Okay. Okay. So before we saw atoms being stretched a little bit during elastic deformation. There's still some point of recovery. Upon plastic, you could see there's some bonds that are broken and it's not recoverable. It's not going back to the original structure. Okay. And you could see also in this cartoon there's a little bit of elongation just like in the previous cartoon. Okay. I included this in here just as a notation reminder, but we don't have to go over it again. We also went through this example. Okay. And just to review what I went through pretty quickly towards the end of last lecture, when we talk about the strength of a material, we're talking about the yield strength. And that's where we define as the point of which, for some amount of strain, it defines the point of which beyond that is plastic deformation, below that is elastic deformation. And so you look at the strain in the x-axis, it's given as a fraction, such as 0.00 something, so then you look at the 0.002 placement, or it's given as a percentage, so you look at 0.2% strain. You draw a slope that is parallel to your elastic modulus, and where it intercepts your stress strain curve, that is your yield strength. Okay, so that's it. And the 0.002 notation is historic. That was defined way back as the separation parameter, and we sort of just adopted that as convention. Okay, so let's do an example. In practice, so if you're given this stress strain curve for a ductile metal, and you're asked to calculate the yield strength, how would one do that? And what would be the resulting number? Let me see. All right, I'll show back the question again for those who need to see the answers. Okay. There's about 10 more people. Let's get your answers in, and I'll pause. Okay, 4 more people. All right, 3. All right, count down from 5, 4, 3, 2. Get your answers in, the last 2 people. 1. Okay, let's move on. Okay, so the answer is 325. Let's see what the distribution looks like. All right, actually the majority of you did get it right, but there were 36% of you that said 250. So for those that answered 325, could you share your thought process? One of you? Yes.
On the previous slide, you said for plastic strain was 2%. So
0.2.
Moved over 2% and recreated the slope, and where it intersected with the curve was the yield strength.
Right. So you mean 0.2%.
Or 0.2%.
Yeah, but your methodology is correct. Yeah, I think you just misspoke. Yeah, so if one were to draw a parallel line, it would look something like that, eyeballing. And then, so where it intercepted, that is your yield strength. And thus, it's about between 300 and 350 if you draw really poorly like I did, right? It's definitely not below 300 and definitely not above 350. So you can sort of estimate in some ballpark, yeah. Yes. You go to 0.2, and let me go back to the lecture slide. Right, so you look at 0.002 if it's given in fractions, or 0.2%, which is the case for the top hat question, and just draw parallel. It's really, this convention has historic reasons because we don't have an analytical equation for modeling this type of behavior. Obviously, you can always find something that comes close to it, but where this bend is, it's not always so definitive. So that's the convention. Yes, Kevin?
What wasn't a plastic? What was like a soft metal or something like that?
A soft metal, what do you mean?
Like aluminum or something that bends easily, or something that will warp rather than breaking outright.
So aluminum would just have a lower yield strength, but it would still have the same ductile behavior, and thus you would apply the same convention. So the question there is, what happens to aluminum? What if it warps instead of experiencing that sort of elastic plastic deformation? And I would say aluminum falls under this category. Its stress strain curve looks quite similar to this type of curve.
That bends, you use the 0.2%.
So that would be a macroscopic bend. So when these measurements are done, they're typically done in a way that the stretching is in one direction, and then fracture will just occur. So there's really no bending per se. It would just be stretching. So it's basically just controlling your variables so that you just look at the lengthening or the cross section.
The 0.2% only works for plastic deformation, is what you're saying?
Well, it works for materials that experience this type of stress strain curve. So it has to undergo elastic to plastic deformation. Where this would not occur would be for ceramics, where you just have elastic deformation and then you have fracture. There's really no plastic deformation. Steel, yeah, so this would work for steel, ductile material. So a lot of metals. The curve for polymers we'll talk about in a little bit. They sort of follow this trend, but the plastic deformation region is actually quite, covers much more strain than, say, a metal. But it would still hold. Okay. All right, so we talked about upper yield point, lower yield point. This is, once again, for a ductile type of material, not really ceramics. We'll talk about necking in a little bit. But before that, we'll talk about ductility. So we covered this very briefly as well from the last lecture, where when we talk about a ductile material, we talk about, right, this plastic deformation. So this would not really occur for brittle materials, although, well, we would just say your brittle material is not very ductile, right? When we talk about ductility, we talk about elongation of the sample as well as area reduction. So, or reduction of area. Sometimes it's AR, sometimes it's RA, but it's area reduction or elongation. And you've seen this before, right? You've seen the delta L versus L naught. That's just your strain. But now we defined it as if you were able to stress your material until right before the point of fracture, right before it breaks right here, okay, or right here. Right before that, and you trace back to where the strain would have been, permanent strain before failure, then we talk about, that's where we define the strain for the ductility of the material before fracture, okay? And so the convention for defining what is a ductile material versus what is not a ductile material, when you calculate the elongation percent, if it's higher than 5%, it's a ductile material. If it's lower than 5%, it's called a brittle material, okay? So once again, just by convention. So you could think about if you start out with some initial length and it changes to some final length, LF, as some people noted, or just L, right? You could also think about some area, there's some cross-section that was at the beginning, and then now there's going to be some reduced area, okay? So it's just a little bit smaller. You can refer to it however you want when you're talking about ductility. Okay. So that's just the technical definition. And then we also talked about toughness, right, or work of fracture. So this is the amount of energy, just like when we're talking about bone and tendon, that's the amount of energy that's required to break your material for some volume material. So once again, we just look at the area under the curve. So the area under the curve for the elastic region for some ceramic here, right, is much less than that of let's say E for ceramics. or I should say epsilon, sorry. For some ductile material, this is the fracture point. And then if you have low strength but high ductility, you can also have low toughness relative to the ductile metals. And so a good example of that are basically most polymers. So here, the point of fracture, E for, let's see, polymers down here. Okay. So that's what we mean when we say a material is tough. We're talking about the area under the curve. Yeah?
The line you're using to close off the area under the curve is
Mhm.
going to have the same slope as the beginning of the arc, correct?
It does not. So where you get the epsilon of the epsilon at failure to get your ductility value, that's E sub F. When we're talking about ductility, you are correct. It is the same slope, right? Let's say those are the same slope. Epsilon at failure. But you're basically extrapolating. You say, if it were to fail and I have some elastic recovery, because once it fractures, there's going to be some elastic recovery. That is why you have this, that's why you trace back to the strain with the same slope. But when you're doing the area under the curve, when you're computing that, you're actually taking the entire strain. So you go out all the way to where the line just drops down, and it is not parallel to your modulus. Because then it would have just fractured. Yeah. So that's the convention. Yeah.
I'm sorry to clarify this, but could you clarify exactly what ductility means again?
Yes. Ductility is just basically the strain, right? To measure it, you're comparing strains. So you're saying that a material is ductile or more ductile than something else is if the strain at the point right before failure is higher or lower than another material. So in this example here, this value, right? This value is higher or larger for a ductile material. So the percent elongation is going to be more than that of a material that's not ductile. So say a ceramic, that's all. Okay. In the interest of time, I may come back to this. Okay. Plastic strain failure. Okay, sorry. I'm trying to get this over. Oh, oops. Let's look. Speaking of ductility, let's practice that. Well, actually, I think this is ductility 2. Yeah, this is ductility 2. So if you had 3 stress strain curves, okay, called A, B, and C, it says here 4 materials, but the last one was deleted. So if you're given a generic strain curve like this for these 3 materials, and you're asked to rank the curve by increasing plastic strain at failure, right? So your first answer would be lowest plastic strain at failure, and then the last answer is one with the highest plastic strain at failure.
Strain is the same as strain on the x-axis, right?
Mm-hmm. about 20 people left. Let's get your answers in. Okay, about 10 people left. Okay, 7 people left. All right, let's get your answers in 5, 4, 3, 2. Last 4 people. All right. I was very generous with relativity of time here. Okay, so what do we think it is? I guess we'll see. Okay, let's see. Okay, overwhelming majority of you got B, A, and then C. So what you're looking at in terms of the plastic strain, right, is you're just tracing that down. This really doesn't have much strain at all, if one could call it that. Now I've said ceramic, stress strain curves for ceramics look like this, and there's basically none. So if you take it at that, the value is 0, right? And then A, and then C, yeah.
Could you actually reopen this? I didn't notice. I'm not lying here. I generally hit the wrong button and didn't notice.
Oh, okay. Email Natalie. She'll fix it. Okay. Okay. Just in the interest of time. Okay. There's a lot of questions, but I do want to get to some of the major points, and we can always go back and practice if need be. Okay, so when we're designing materials, we have design safety factors, so that basically we over-engineer a system. So if we know a material's yield strength, this sigma y, right? For some material, here the example is a 1045 steel rod. And if we know that it has to withstand some sort of applied force, and if the safety factor is, let's say, 4. Now, these safety factors are basically how much you need to scale by so that you can withstand a certain applied force. So if you're designing a chair, say, something like that, your design safety factor is probably going to be much lower than that of a material if you're designing, for things like bungee cords or engine blades, things like that, right? So there's a variation in the factor of safety, and for that reason. So basically, you just multiply your applied force or divide your yield strength. So here in this example, if you apply a force of 220,000 newtons, right? And your safety factor is 4. You're essentially saying, I need a material that has that can withstand 4 times that, just so I over-engineer and I don't get fracture, so close to the amount of applied force that this material is going to experience in service. So the way you would use or apply a safety factor is, if the safety factor is 4, you can say, okay, well, this material has to withstand 4 times the amount of force, so you just move the 4 over here, and you basically just multiply and scale so that you just over-engineer. And that's basically it. So then you can, in this particular example, it's asking you to calculate the diameter of a rod that you would need to ensure so that the yield doesn't occur until you reach this, or it could withstand 4 times the amount of the applied force, and that just happens to be, if you work out the math, it's 6 centimeters. So this is, the first approximation for designing steel beams and whatnot, Okay. Now, let's talk about permanently deforming a metal. Okay. When we talk about plastic deformation, we talked about the atomic structure changing, right? The atoms are moving, bonds are being broken, so we talked about that. Let's now talk about the strength of a material. When you plastically deform a material, you'll actually make it stronger. So deformation is not necessarily a bad thing. When we take a look at this stress strain curve, we say, okay, if you deform a material within its elastic region, okay, somewhere here, let's say that. Beyond that, you're plastically, sorry, let me switch colors. Beyond that, you're plastically deforming your material now. So you could see that the strength of a material is actually increasing as you deform a material. So a good example of demonstrating that is just taking some material. This happens to be copper, but you could also do it with aluminum or any metal. So if I may have 2 volunteers to demonstrate strengthening of a material through plastic deformation. Come up front, please. We got 1. All right, we got Ethan and Zachary. So we'll switch roles. First, you're going to plastically deform the copper rod by bending it, let's say. Okay, you're applying some force. Obviously, this is not dog bone, nor is this the standard by any means. So what Zachary has done is he's introduced a whole bunch of dislocation by working this material. So he's increased the strength. How much so can Ethan undo that strength? Okay, remember your bone fracture? Let's go back to that plot.
Okay.
You can see it's quite difficult, right? The ease of which Zachary could apply a force and introduce dislocation versus now the increased strength of a material makes it much more difficult for Ethan to undo it. Let's do it the same for, this is 3/8 inch, by the way.
I don't think I can get this anywhere.
You can do it. Okay, at some point, I chose a thickness that was too thick, sorry. Okay, all right, so if you apply enough force, maybe the answer is you can deform a material and introduce a whole bunch of dislocations. Ethan? I'm just kidding, I can't even, this is why I asked for volunteers, because I myself cannot undo this. So thank you very much. I'll give this back to the machine shop and they will re-anneal and straighten this out. But thank you very much for that demonstration. So you can see when you deform a material, you actually increase the strength, because when Zachary let go, he let go of the load that he was applying, right? And so now you could think about coming back, sorry, I'll definitely get to you, just one moment. You can definitely think about, okay, so Zachary has now deformed some material, the strain is somewhere here, he's let it go. That's supposed to be a straight line. He let it go. And now, you could see if you draw this material again, there is some plastic deformation that's restored when he lets it go. And then if you continue the curve again, you could see the strength is now increased a little bit. And you can actually just continuously do this, but then at some point you strain too much and you will actually cause fracture. You can do this at home too. If you don't have a machine shop, well, 1, you can just buy this, by the way, off of like Amazon. But 2, you could also just take a paper clip and the same idea occurs, right? I mean, you can do all sorts of designs with your paper clip, and if you just keep on going and going and keep on twisting, at some point it's going to fracture. There was a question, 1, 2, and 3. Yes and no. So yes to both. So right. So this is I agree with that, because this is an imperfect example of introducing dislocation, right? I think the better and more consistent example would be what you've seen with necking, where you're just elongating and then you actually reduce the cross-sectional area, and that's when it starts to neck. So when you recalculate the force over area, you're actually dividing by a small area, so your strength actually increases. Sigma equals F over A. When you decrease A, right, sigma goes up because you're dividing by actually a smaller number. So that would be an example that would be a little bit better than, say, adding an angle to this sort of example. So yes, I agree with that.
How do you explain the phenomena on the Thomas scale? Is it just that not in this example, but the area
The area decreases in the?
this amount of force applied to strain the material increases, is that?
Okay. So in this particular example, you're introducing, yes, dislocation, you are plastically deforming by a little bit, but not to say this extent that a machine could, apply a load and neck a material. Certainly, the material really hasn't been necked, right? There's really no appreciable by the naked eye, change in the cross-sectional area here based on the applied load that Zachary applied, right? But if you do keep on increasing that load, increasing F, right, or you will be able to get to a point, if it's just straight, you will be able to get it to a point where the material will start to neck.
So how can we explain the differences in the requirements of force after plastic deformation on the atomic scale? Like what's happened to the atoms that you said there isn't much making occurring here?
Right. There's not right. There's not a lot that's occurring here, but in terms of atomistically, what's happening is that there's a number of mechanisms that we'll talk about. Slip is one of them. So this happens to be FCC, and so the atoms will start to move, as you've seen in the cartoon. The atoms will start to move, and bonds will actually start to break. And so with that, that's elongating the material there. We can follow up if that's not 100% clear. There was a question in the front and back. Do you still have your question? Yeah.
Is that deformation similar to cold rolled steel?
Yes, absolutely. Is that deformation similar to cold rolled steel or cold working or strain hardening? Absolutely.
Do the grain boundaries
The grain boundaries
change? Is that
do change-ish. Okay, so I'm only hesitant to say that because I don't think Zachary applied enough, force to really change the grains per se. But in the example that Nathan asked about, when you're rolling a material, you are changing the grain size per se. That's one mechanism. Another mechanism is to heat a material, to change the rate of solidification, to change the grain size. That is something we'll talk about in chapter 10. I wouldn't say that there's a significant amount of grain size changing just based on this example. But yeah, you can definitely do that. And that will change and enhance, that will increase the strength of a mechanism, the strength of a material by decreasing the grain sizes, right? Because then that increases the number of grain boundaries, and that will actually impede dislocation movement, and thus your material will be stronger. And that is something that will come up in about 10 slides or so. Yeah. Okay. The one thing I didn't note in this example, but you see here on your slide, is that it says ductility will decrease. So if you keep on doing this, maybe this, if you keep on actually increasing the strength, your ductility will actually decrease as your strength increases. So what happens is then you'll get something that looks like, so if you cold work or strain harden, as Nathan asked about, the percent of which you do that, the percent of cold working or strain hardening, your curve will eventually start to look like this, where ductility will decrease, but strength will increase. Okay, so that's something to note. Okay, right, there was a discussion of necking and atomic structure. We touched upon that briefly, where we say materials do become stronger in the neck, because if you're applying the same amount of force to it, your area is becoming smaller in the necked area, and thus your yield strength will increase. Okay. So if your new area, if this is your initial area, if this is a smaller value, your sigma will actually go up. Okay, but what you see here in this plot is after the start of necking, we still normalize by the initial A naught, so by the initial cross-sectional area, and so you see it actually going down. So in reality, if you're plotting a true stress curve, you'll actually see something that looks more like so, and you probably have come across it, something that looks like this, if it's the true stress, because now you've normalized by the new A, okay? Yeah, so you may or may not have seen it if you're working in a lab that makes these kind of measurements. Okay. We talked a lot about metals, bones, tendons. Let's focus now more on ceramics. And of course, alumina is a widely used example because we use alumina in, well, one, we use aluminum in everyday life. We also use alumina in everyday life. It's a great refractory material for absorbing heat. If you work in, say, a lab that uses a lot of furnaces, sometimes you just see like blocks of alumina to, put your hot samples on, things like that. You could also use it in lasers to, control path of light. And so there, we're talking about single crystal alumina. We refer to it as sapphire. So when we talk about ceramics, we don't really do the same types of tests on ceramics as we do metals. We can't really make a dog bone, out of a ceramic piece of material, mainly because as you've seen from the stress strain curve, there isn't going to be plastic deformation. You're just going to get a fracture. So what people typically do to test the strength of ceramics, they typically do these 3-point tests, or sometimes you maybe have seen 4-point tests as well, to calculate the modulus of rupture, or its where it's going to rupture. So we won't go through this top hat question, but I just want to outline, if you apply a force, this way with 2 counterpoint forces at this location here and this location here, we can calculate this modulus of rupture if we know the dimensions of your specimen. So if you have, let's say, a bar of alumina or a bar of silica, or here soda lime glass, if we know the dimensions, we can calculate the MOR by just using this convention, where it's just 3 times the amount of applied force times the length of your material divided by 2 times the thickness and also the height squared. And so you can tell somebody, the modulus of rupture, or the amount of, or you can calculate the amount of force that a material or ceramic can withstand before it fractures. Yeah.
Ask them L again, because L is morning.
Yeah, L is just length. It's not drawn on here. Oh no, I'm sorry. It is drawn on here. I just didn't see it.
Again, is that the force being applied?
Yeah. Mm-hmm. Mm-hmm.
What's that top circle?
Oh, it's where you place the point of contact for the force. It's just like enlarged. Okay. Let me see. Let me see if I have time for slip plane discussion. I'll briefly get started, and then this is where we'll pick up next time. But the point of slip and how does deformation happen is actually quite important to know for both single crystals as well as polycrystalline material. Because if you're asking, well, how much stress can this material experience before fracture, right? So before that, during plastic deformation, these atoms are moving, and there's a particular mechanism of movement, and it's called slip. And when we talked about FCC type material, BCC type material, we talked about the planes of which the atoms are close packed. So the planes of which the atoms are touching. So in that case, we're talking about the 100 plane of FCC, the 111 direction of BCC, right? Those are the planes and directions where the atoms are touching. And so those will also be the directions in which these atoms will also slip past each other. And that's how all these deformations are going to happen in metals. And so an example here is zinc HCP. And you could see the basal plane. So we didn't go into depth about basal planes, but of HCP because we only focus on FCC, but the gist of it is that in the plane, and you're not going out of plane, in the plane, the atoms are close packed for hexagonal for HCP systems. And so you could see the slip is happening all along that direction for single crystal zinc, that's HCP. And so we can actually calculate for a polycrystalline material, you know, what is going to be an amount of stress that a material can experience, you know, before fracture, things like that. Okay, since this is going to be a lengthier discussion, I want to stop here and pick up on it on Wednesday.